Alrighty, so this video is going to cover what's called the method of undetermined coefficients. And as you may notice, that instead of having a homogeneous differential equation, we now have a non-homogeneous second order constant coefficient differential equation. Now, as we progress in the course, we're going to ask, what happens if these aren't just numbers? What if these coefficients aren't just numbers? Maybe, we might try and see, is there a way we can handle nonlinear versions? But for now, we're still handling linear second order constant coefficient differential equations. But we just maybe have some function here at the end. And the question is, how do we go about solving this? And so what we mean is, for example, let's say I have a differential equation like y double prime plus 2y prime minus 3y. And then I now, instead of having 0 at the end, I tack on some other solution. And so for the sake of doing examples, I'm going to put a whole bunch of different types. So I'm going to say, what happens if I have like e to the 7t, maybe I'll put like 4e to the 7t. What happens if I had, that this equals, let's do 3 sine of I don't know, 8t. What happens if we had that this was equal to, I don't know, t cubed minus 3t plus 4. Maybe we'll do one that's a combination. What if we have, t to the fourth, maybe 7t to the fourth, e to the 6t, stuff like this. And I'll expand this list as we go on. The question is, like what's different now? Okay, what has changed? And so the big idea here is that unlike in the homogeneous version where we just set all these equal to 0, we got a characteristic equation, we solve for the homogeneous equation, we solve for the homogeneous solutions. Now we have these extra little functions on the right-hand side. And our goal, is how on earth are we going to come up with the particular solution for this differential equation? Right, we have a particular function on the right-hand side, and just like with the homogeneous version, we are going to make educated guesses as to what our solution is, and we are going to guess that our solution to this, what we call our particular solution, which I'm going to denote y sub p, is going to look something like this function. Now, why would that be an educated guess? That's an educated guess because if you really think about it, like what function could I plug in for my y double prime, y prime, and y? What function could I come up with whose first derivative and second derivative and the original function are all going to combine to give me some amount of e to the 7t? Following the logic from the homogeneous version, we would say, well, the only one that kind of makes sense would be like some a e raised to the 7t, like that's literally only function, right? You can't put sine in here because if I put sine in here and then I get what, cosine and then negative sine, those aren't going to cancel out to leave me e to the 7t. The only function that's going to make sense to make a guess here is a times e to the 7t. And we're going to follow this trend for the rest of them. We're going to follow this trend. So what happens if we have a sine function like 3 sine of 8t? Again, we're going to make an educated guess. What kind of function could we have? And it turns out that, it might make sense to write a sine of 8t as a guess. But the problem is that the derivative of sine is cosine. And there's nothing that we're going to get here that's going to magically get rid of that cosine for us and leave us with, 3 sine of 8t. And so what we do for our guess for anything involving a trig function like this is that we guess that there's also some b cosine of 8t that is part of this solution. Okay, this should make sense because the derivative of cosine is going to be sine, the derivative of sine is going to be cosine, and the derivative of cosine is going to be negative sine. And hopefully we imagine that some mix and mash of that hodgepodge of sines and cosines is going to leave us with 3 sine of 8t when we're all said and done. And so this is like the educated guess that we're going to make for the solution for something that looks like this. All right, so following along with this particular logic, let's kind of go down to t cubed minus 3t plus 4. What kind of educated guess are we going to make here? Well, the question is, what kind of function do we have here? We have a polynomial. We have a polynomial of degree 3. And so you might say, okay, well, it's not going to be a sine function or an e function because, like, that wouldn't make sense to plug in a sine function up there, and I'm not magically going to get left with a polynomial. The only thing that would work is if I guess some other polynomial. And now the question is, what polynomial do we guess? And it turns out in this that we're going to guess some generic cubic polynomial. So at cubed plus bt squared plus ct plus some d. We're going to guess that our particular solution is a generic cubic like this. Now, people have a couple comments. They say, well, there's a bt squared here. There's no t squared in here. The idea is that hopefully, right, somewhere along the line, when I plug in this function in here and I plug in the derivative here and I plug in the derivative here, that any t squareds that we get are going to cancel out and disappear in this project, in this process. And you might say, well, why didn't we pick like a t to the fourth, right? Why didn't I pick something raised to the fourth power? And for a very similar reason, if I put in something here to the fourth power, all the derivatives are going to be less than that power. And so we'd end up with like a t to the fourth in our answer, but there is no t to the fourth over here. And likewise, you can't get this t to the cubed, this t cubed term to show up unless our proposed solution also has a t cubed. So we make this educated guess that if we have a polynomial of degree 3, that our solution is probably going to look like a polynomial of degree 3. Now, I am saying this stuff without any justification. We'll go through and do a couple examples, but just to kind of get a pattern for what the heck's going on. So again, for this last one, here I have something interesting. I have a very small 4th degree polynomial, and then I have an e to the 6t that's kind of been attached to it. And so what might we guess for our solution? Well, it would make a lot of logical sense to guess that that our solution is going to look like y sub p is equal to some 4th degree polynomial at to the 4th plus bt cubed plus ct squared plus dt plus e. And then we're multiplying this by e raised to the 6t, right? That we guess that our solution is going to be some 4th degree polynomial multiplied by e to the 6t. And you might notice there's no f here, right? There's no f in front of the e to the 6t because any constant that I would just put there would multiply in with all these constants and just create new constants anyway. So I don't need to throw in like another coefficient in front of that e term, right? We already have this long polynomial there. And again, the reasoning is the same. Why do I need to include all of these other terms that are not a t to the 4th? Because if I don't, if I only guess that my solution would look like a t to the 4th, e to the 6t, we know that when we take the derivative of this, a t cubed is going to pop out. And when I take the derivative of t cubed, a t squared is going to pop out. So if you think about it like that, then it should kind of make sense that our guess would have, a t to the 4th, a bt cubed, and a ct squared, because those things would need to cancel out. But then if you include these in the original, guess for our function, those derivatives are all going to go down 1 power, 2 powers, etc. And so it turns out, just to cover all of our bases, even though we just have one single term from a 4th degree polynomial here, just this 7t to the 4th, we need to kind of bring all of these along and hope that when we're solving this, that things kind of cancel out and so on and so forth. And this process kind of follows along. So, if you feel like you're getting the hang of it, what if this ODE, what if our differential equation looked like, 2t, let's just do 2t times e to the 4t times cosine of 10t, something like this. Our guess would, we just kind of follow along. We say, okay, well, there's a polynomial, there's a linear term right there, so we're going to toss in this linear term of at plus b. Then there's a Then there's this e to the 4t, so that kind of gets thrown in. But now the question is, what do I do with this cosine of 10t? And the answer is it's very similar to what we did earlier with the sine of 8t, which is, you know, we would typically have a you know, a just like we did before with the sine, we'd have like an a sine of 8t and a b cosine of 8t, something like so. And so the way we're going to do this is in a very similar fashion. I'm going to put on a sine of 8t right here. But then, you know, we're going to have this plus cosine bit as well. And it gets its own little set of a polynomial and an e to the 4t. So it's going to get like its own ct plus d times e to the 4t times cosine of oops, I didn't mean to write 8t earlier. I meant to write 10t because we're using a 10 now. 10t, there we go. And this is what we're going to get. This is going to be our educated guess as to what our solution is this time around. And these patterns generically hold, you know, for any of the problems. These are about as crazy as we might get. There's nothing too crazy. So, for example, let's do one. Let's solve the let's solve the first one. Let's do this one together. Okay. So if we solve this right, and we were to you know actually go through this problem, how do you verify that anything is a solution to a differential equation, right? If we guess that this is indeed a solution, how do you check it? You just plug it in and you hope that it works. So we're going to guess that our particular solution is a e to the 7t, which would make the derivative 7a e to the 7t, and it's going to make the second derivative 49a e to the 7t, and we're going to start plugging stuff in. And so we're going to get, for our differential equation, if we plug everything in, we're going to get 49a e to the 7t plus 2 times my y prime. So 2 times that is going to be a 14a e to the 7t, and then minus 3 times the original thing, so minus 3a e to the 7t, and this should hopefully all equal 4e to the 7t when the dust has settled. So if we do a little combining, we get 49 plus 14, which I believe is 63, minus 3, so we get 60a e to the 7t is equal to 4e to the 7t. And from here, we can use this technique called balancing coefficients. Now, I know that we could go through and do some algebra to solve this, but this cool technique says, you know, well, how many e to the 7t terms do I have on the right side? I'm going to make a note of this. How many e to the 7t terms do I have on the right side? The answer is I've got 4 of them, so I'm going to write a 4 here. And my question is, how many e to the 7t terms do I have on the left side? And the answer is I have 60a of them. And so this allows me to very quickly solve and get that a is equal to 4 over 60, or we could simplify this and get 2 over 30, which is 1 over 15. And so there we go. We've solved for a, and thus we have solved for our particular solution, that this function does indeed solve this differential equation for a is equal to 1 over 15. Now that's a pretty easy one. It reminds us a lot of our homogeneous approach. So let's do one that's a little less simple. Let's do the a sine of 8t and b cosine of 8t approach, right? So let's rewrite this differential equation. As an example, we'll do y double prime plus, what was I using before? 2y prime minus 3y is equal to, and now we're going to make one up. So let's see what we're using. 3 sine of 8t. 3 sine of 8t. Okay. And we're going to make an educated guess that our solution is of the form a sine of 8t plus b cosine of 8t. And if you like to write it the other way, if you want to write a cosine and plus b sine, that's totally fine. That's kind of how we write things when we use Euler's formula. Totally up to you. But we're going to get that the derivative, all right, so is going to be 8a cosine of 8t minus 8b sine of 8t. And then we're going to get for the second derivative, y double prime, we're going to get a negative 64a sine of 8t. And then we're going to get minus 64b cosine of 8t. Okay, so when we put all of this stuff together and we start to stitch things together, we're going to get, let's see, so y double prime, I'm going to factor out that negative, forget it, we'll just leave it. So negative 64a sine of 8t minus 64b cosine of 8t, that's our y double prime. Now we're going to do the 2y prime, which is going to give us a plus 16a cosine of 8t minus 16b sine of 8t. All right. Then we're going to need to subtract 3 times the original y, so minus 3a sine of 8t minus 3b cosine of 8t is equal to 3 sine of 8t, right? In theory, if this all works out, we should get equality. So let's combine some stuff here. Let's see what we got. So let's see. I have how many sine of 8t's do I have on the left side here? I'm going to take note of this. Sine of 8t. All right. How many do I have on the left side? I have negative 64a here. I have a minus 16b of them here. I've got a minus 3a of them here. So I'm going to write all this down. So minus 64a and then a minus 3a. That's going to give me a minus 67a. And then I have the minus 16b from over here, minus 16b of them. And that should equal the 3 that I have on the right side. So this should equal 3. Okay, now how do I know this? Because I'm claiming that this is a solution. And if this is a solution, I should plug all of this stuff in and I should get everything that's on the right-hand side. And so all I'm doing is I've plugged it in, and at this point, we are assuming that both sides are going to be equal by necessity. We're assuming that this is a true statement, which means, I can look and say, well, how many sine of 8t's do I have on both sides? There they all are, right? And then I can ask myself, how many cosine of 8t's do I have on both sides? And so, again, I'll take note of this. So how many cosine of 8t's do I have on both sides? And I have a minus 64b, I have a plus 16a, I've got another minus 3b of them, so that's going to give me a minus 67b of them. And then we have the plus 16a of them on the left side. But how many do we have on the right side? Well, on the right side, we have none of them. This should equal 0. And so now, right, to basically, finish this problem, we essentially just have this very small system of equations that we can solve using a whole bunch of techniques from algebra 2, from linear algebra, if you feel so inclined. But I could take this and I could say, take the first equation, and I could say that negative 67a is equal to 3 plus 16b. I could divide out that negative 67, so a is equal to 3 plus 16b over negative 67. And then what can I do with this? How does this help me? I can plug it back in to the second equation here. And so my second equation is now going to be negative 67b plus 16 multiplied by 3 plus 16b over negative 67. And that should equal 0. And so, there's a bazillion ways you can do this. You're going to probably need a calculator for these particular numbers because I didn't plan them ahead of time. So let's just see what we get. If I were to try solving this, I'd probably multiply both sides by negative 67 just to clear fractions. So I'd end up with 4,489b plus 16 times 3 plus 16b is equal to 0. And I'm going to combine some like terms. So I'm going to see, I'm going to have 16 times 3. That's going to be 48. And then I'm going to have 16 times the 16. So 16 times 16, which I'm then going to add to the total number of b's that I have over here. So 16 times 16 is 256. And then if I add that to my existing b's, I'm going to get 4,745 b's. And this is equal to 0. And so we're going to get that b is equal to negative 48 divided by 4,745. I don't know, is that divisible by something? Let's try it out. 4,745 divided by, is that divisible by 8? Nope. How about 686? Nope. Okay, I'm just going to leave this as is and say that this is my b, right? And I know, well, how do I get my a? There's my a, I can solve for it. And for the sake of not getting too lost in the algebra, because that's not really the point is that when all of the dust settles, I can solve for what my a is. I have already solved for what my b is, and thus I have created the particular solution. It turns out that to get all of the pieces to cancel out and to get all the dust settle, my particular solution does indeed look something like this, with very special choices, very particular choices for these a's and b's that go right here. And so this is it. This is what's called the method of undetermined coefficients. It's you plug in everything and you do kind of some balancing. You say, well, how many sines are on one side? How many cosines are on one side? And you can do this process fairly universally. And I did it before in the previous problem where, when we were over here and I said, well, how many e to the 7t's are on both sides? Once I had plugged everything in, I said, oh, there's 4 of them on this side. And then I smushed them all together and said, there's 60a of them on the left side. And we solve for a fairly quickly. So this is the general process for doing this. This is our general process for guessing for these. But as always, there's a slight catch. There are some what we call special cases, okay? So there are special cases where we need to modify our guess slightly. To modify our guess slightly. Okay, and so here we are. Okay, so what happens? There are basically 2 big special cases. So as a reminder, remember that when I have an ODE, right? When I have a second order ODE and we equal some f of t, there is a on the left-hand side here, there's a differential equation and we can solve for its homogeneous solution. And the way that we usually did this in the first case, case 1, which is, that r is equal to some numbers, right? Maybe I'll call it r1 and r2, okay? So where these are real, okay? R1 and R2 are real numbers. Now, in the case of solving for homogeneous solutions, we ran across the issue, for instance, like let's say r was equal to 2 and 3, then the homogeneous solution would just look like C1 e to the 2t plus C2 e to the 3t. And in the case that, let's say, r was equal to 2 and there was a multiplicity of 2, right, where basically the root repeated itself, we said that the homogeneous solution was like C1 e to the 2t, but instead of writing the same thing twice, we slap on this extra t because we had multiplicity, right? This was kind of like the trend. And so there is a similar trend when it comes to making a guess for a particular solution that already looks like the homogeneous solution. So what do I mean? So let me on the right side, let's just make one. So let's say I have some ODE. And we'll use the green case as an example. So in the case where our differential equation is equal to, say, let's say it equals 4e to the, or actually here, let's make it interesting. 4 t cubed minus t times e to the 3t. Okay, let's say we have something like this. So, your very first natural guess for the particular solution would be that y sub p is equal to some cubic, so at cubed plus bt squared plus ct plus d times e to the 3t. This would be a very natural guess. But I claim, or so the textbook claims, and again, you can pop open the textbook. It's on page it starts in page 178, I think, and it goes to 180. There's like a 2 or 3 page proof onto why this is if you're interested. But the idea is that since e to the 3t in this particular case is already taken, there's already an e to the 3t there, right? It's part of the homogeneous solution. It says take your guess and do exactly what you did before. There's already an e to the 3t. You're going to slap a t in front of this thing, okay? And you might say, that there's, well, Dylan, there's already a bunch of t's in front of this thing. I'm just gonna shake my head and say, look, listen, there's theory, there's the textbook. If you want to read the theorem yourself, it's on page 180 of the text. The theory just says, if you ever need to make a particular solution, and it involves, an e to the some power, and that in this case, e to the 3t is already taken, you need to modify your guess to have a t there, okay? It can't just be that, e to the 3t is our guess here. It's going to be that t e to the 3t is our guess. And so in the same sort of way, if I have an ODE, now let's go on to this pink example. If my ODE is equal to, again, let's say 4t cubed minus t e to the 2t, and in this particular case, we notice that, when I solve the homogeneous version, right, and we solve for the characteristic polynomial, we get r equals 2 as a root with multiplicity of 2, then it turns out, well, this has been taken 2 times, right? It already shows up in our homogeneous solution twice, and so it turns out that not only do I need 1t when I make my guess, but that my particular solution guess is going to have an extra t squared in the front of it to accompany the cubic that we would naturally guess, at cubed plus bt squared plus ct plus d times e to the 2t, okay? So this is the first, wacky case where, in 99% of what it is we're going to do, this may not happen, but, the textbook likes to throw you the curveballs, and so I'll say that one of the curveballs is just if, we have e to the 3t, e to the 2t, e to the rt in our guess already, right? It's already part of here. You have to see how many times it shows up. If it shows up once already in the homogeneous solution, we've got to throw in an extra t to differentiate it. If it shows up twice in the homogeneous solution, we've got to throw in 2 extra t's to differentiate our guess. And this we're just going to say is the math god's law, okay? So this is our first special case where r is a real number, but you may remember that we don't necessarily just have real solutions. So in case 2, when solving these ODEs, when we're solving for the homogeneous solution, we can get the case where r is equal to a plus or minus ib, right? Where we basically get these complex roots, right? And it results in our solution, our homogeneous solution, to look something of the nature of a e to the at cosine of bt plus b e to the at sine of bt. And that's our solution. Or if you prefer, you could factor out the e to the at first and just write it as a cosine of bt plus b sine. Sorry to use the same letters just in lowercase and capitalized form, but this is what it looks like, right? This is our solution. And in the same way, let's say that we have a differential equation, right? We have something like this, and it just so happens that we have 3 t squared times e raised and to, let's give us a tangible example. So let's say we have 2 plus or minus 3i, right? And so our solution then, our homogeneous solution, our y sub h, would be, e raised to the 2t times A cosine of 3t plus B sine of 3t. Hopefully you can kind of pick up the pattern that if my ODE that I'm trying to solve is now no longer homogeneous, but it looks like 3t squared e raised to, let's say, the 2t, and then, heaven forbid, we have like a sine of bt, attached to this. Let's say I have a sine of 3t attached to this, okay? Then we make the very astute observation that, look, we already have an e to the 2t sine of 3t in this problem, and so guess what our particular solution has to get slapped onto it? Our particular solution, guess, will not only have the at squared plus bt plus c for the linear term in the front, it will not only have the whole e to the 2t cosine of 3t, let me zoom out a bit, plus, and then we do this again, so like dt squared plus et plus f times e to the 2t sine of 3t. It will not only have all these components just like we did last time, right? Just like we did before. It's not only going to have all of these, but they're all going to have an extra t slapped on to differentiate them from the e to the 2t sine of 2t and the e to the 2t cosine of 2t or cosine of 3t that we would have already had before. This kind of goes, it goes hand in hand with the idea that our solutions all have to be linearly independent of each other. So we don't want any repetitions where they all just kind of condense. And so this is it. So, if this differential equation, just to kind of, drive the point home, if this differential equation had literally equaled anything else, 3t squared e to the t sine of 3t, because e to the t sine of 3t is not the same thing as these, it's not just that in disguise, our guess would have literally been that our particular solution guess would have been what we thought before. At squared plus bt plus c times our e to the t times our cosine of 3t, and then we tack on the, the other polynomial, dt squared plus et plus f e to the t sine of 3t. That's it. Like nothing else would have changed. You may ask, what if we had that the ODE was equal to 3t squared e to the 2t? You might be, Dylan, there's an e to the 2t here. Yes, there is, but that e to the 2t is accompanied by cosine and it's accompanied by sine. Those are being multiplied to it. And so e to the 2t as a standalone function is a very different function than e to the 2t multiplied by cosine. So our guess in this particular example here is not impacted by our homogeneous solution. Our guess would just be at squared plus bt plus c times e to the 2t. There's nothing that we have to, there's no repetition that we have to be worried about. And so, right, this is basically all the stuff that could go wrong. And so you may be, rightfully so, asking, why do I have to worry about the homogeneous solution? Why is it, why do we have to worry about this at all? I don't even see the homogeneous solution. Well, surprise, it turns out that, so theorem, that for an ODE of the form ay double prime plus by prime plus cy is equal to some function of t, the general solution is denoted y sub g, and it is a result of taking the homogeneous solution and adding it to the particular solution. And you might say, what the heck? We need to solve for the homogeneous solution first, or like as part of solving like this problem. Like, what the heck? Where does the homogeneous solution come in? Well, let me give you a practical answer, and then I'll give you an example as to why. The practical answer is, if I plug in the homogeneous solution into this differential equation, what am I going to get out? It's the homogeneous solution. We get out 0. And then what do I get if I take the particular solution and plug it into this differential equation? I'm going to get out f of t. And so it turns out that by smushing these two things together, number one, it doesn't impact me equaling f of t. Okay, it doesn't change that at all. So it's almost, so on one hand, it's like because we can. But the other more real reason is because this is what we call, the most general solution. It is the solution that encompasses all possibilities of what the answer could be. And maybe to just kind of give you a practical explanation is the following example, which is, consider like this differential equation, y double prime plus 2y prime plus y is equal to x. And let me give you, there should be two initial conditions, but let me just give you one for now. Let me give you that initial condition. And if I tell you, you might notice that the particular solution of x minus 2 solves this differential equation, right? We can easily verify this because the derivative is equal to 1, the second derivative is equal to 0. So if I plug all of these into my differential equation, I get 0 plus 2 plus x minus 2. And the question is, does that equal x? And of course, we do get x is equal to x. So check mark, this is the particular solution. It solves this differential equation. But you'll notice, what does it not satisfy? This solution function, if you were to tell me that the whole complete solution was just x minus 2, I'd say, well, what the heck? Because I have this initial condition. And if I test my initial condition in here, I definitely don't satisfy this initial condition, right? I get 0 is equal to 0 minus 2. I get equals negative 2. This is a sad face. We break math. And so in some way, we haven't come up with a complete solution. And it turns out that the particular solution solves a particular differential equation for a particular initial condition that we may or may not be interested in. In this case, it solves it for it solves it for the initial condition y of 0 is equal to negative 2. Right? If this was our initial condition, then this would be the solution and like life would be good. But in general, I can throw any initial condition, right? I could have y of 0 is equal to 0. And so what the order of operations should be is we should take this thing, and the first thing that we should do, so this is good advice for solving a differential equation like this in general, is step one is we should solve for y sub h first. So in this case, we get r squared plus 2r plus 1 is equal to 0. We factor this into r plus 1 times r plus 1 is equal to 0. And so we get r is equal to negative 1 with a multiplicity of 2. And so this tells us that the homogeneous solution is equal to c1 e to the negative t plus, now since it's multiplicity, we slap on a t here, t e to the negative t now. And this is the homogeneous solution. Okay, that's the homogeneous solution. Now, I gave us the particular solution, but if you want to see me do the process, the second step would be, that we need to solve for y sub p. And now, when we look at y sub p, we need to make a guess based on what this function is here on the right. Now, that is a linear function, right? X by itself is a linear function, just like, don't be fooled if I had an ODE is equal to the number like 7. This is also a linear equation, right? They would both get the guess ax plus b. And so we say, okay, first and foremost, we want to make sure we want to check this against the homogeneous equation. Now, notice that, our differential equation here on the right-hand side, we didn't have like an e to the negative t here on the right-hand side. So I don't need to worry about getting any copies here. I don't need to worry about needing to slap on a t squared because I already have e to the negative t twice as it's shown up here. I don't need to do any of that because the particular solution that I'm guessing for this function on the right-hand side doesn't conflict with our e to the negative t. So that's like the first check that we want to do. And then we're going to run through this and say, okay, the derivative is equal to a, the second derivative is equal to 0. We're going to plug it into the differential equation. So we would get, we're going to get 0 plus 2a plus ax plus b, and this is supposed to equal the x that I have on the right side. And I'm going to go through and balance coefficients one more time. I'm going to say, well, how many x's do I have on both sides? Oh, okay, I have a of them on the left. I have one of them on the right. Bingo, I just figured out what a is. Now, the next question is, okay, how many constants do I have on both sides? Right? How many things do I have that don't have any x's? Well, on the left side, I have 2a of them plus b of them. And on the right side, I have no lingering constants. So we get this second equation right here. But I already know that a is 1, so I get 2 plus b is equal to 0, and so b is equal to -2. And we very quickly get that our particular solution was equal to x minus 2. And thus, we now have, in I guess, step 3, we kind of we stitch together a general solution, which is c1 e to the -t plus c2t e to the -t plus, oh, I've been using t's. Whoops. I've been using x's. All right, I'll change them. Downside about making online videos is no one's here to say, Professor, these are supposed to be x's, plus x minus 2. So now we have a general solution, but notice that we have unknown coefficients c1 and c2, which means in our differential equation, we should have been given an initial condition of some sort in the form of y of something and y prime of something, right? That's usually how we get our initial conditions. And we would solve for c1 and c2. And in this example, I'd already said it, right? I gave y of 0 was equal to 0. In order to solve for two unknowns, I would need two initial conditions. So maybe I know that y prime of 0 is equal to 3. And now I can solve for the precise general solution that has these as the initial conditions. And notice that I'm plugging these initial conditions into the general solution. I'm not plugging it into just the homogeneous solution. I'm going to plug them in to the general solution. So for instance, right, we're going to get 0 using the first initial condition is equal to c1, I guess e to the 0 is just 1. And then this is 0, this is 0, so we get with a minus 2, so c1 minus 2. So what do we get? This tells us that c1 is equal to 2, so I'm going to lock that up. And then using the second initial condition, we need to take the derivative of all this, and I'm not going to do it for the sake of time, but we take the derivative of this and we solve for C2, and then we're done. And then we have a final general solution, okay? So we talked about a lot in this video. I'm going to very briefly recap it all from the start. So we introduced this method, which is basically how we solve these second order constant coefficient linear differential equations that equal now not just 0, they're not homogeneous, they are non-homogeneous, they equal some function. We came up with a general process for guessing solutions, right? We talked about what to do when you have a whole bunch of stuff multiplied together. It's pretty easy to follow the trend. And then we tackled, what happens in the various, like what do we guess basically if it just so happens that our guesses are already kind of part of the, they're already part of the homogeneous solution, okay? And so we covered the two cases, right? What happens if our guess involves the homogeneous solution when there's multiplicity of 1, right? When there's one root. What happens if we had repetition where there's two roots? And it involves you slap on a t or a t squared to kind of to create a unique particular solution guess. And then we also tackled the very, very, very hyper-specific case that our differential equation equaled something that was already taken into account for in our homogeneous solution again. And since the maximum number of times this could happen is 1, the worst case scenario is we have to slap on an extra t. But I went through some examples here where that doesn't happen, where we don't need to slap on an extra t. I talked about, that in general, so the entire answer, the full complete answer to one of these problems is the general solution, which is the homogeneous plus the particular solution. And I went through the idea of, why isn't it just the particular solution? It's not just the particular solution because that may not satisfy our initial condition. So we include the homogeneous solution, number one, because it's free to add. We're just adding 0 essentially. And 2, because it creates a complete solution. And then I gave a step-by-step process of, look, if I were to solve one of these problems, this is what I would do. Step 1 is you always start solving the homogeneous solution first, because you cannot make your guess for the particular solution unless you know what your homogeneous solution is, because you don't want to accidentally guess something that has already been used in your particular solution. So you basically need to watch out for those fringe cases that I mentioned before. And then once you have your particular solution guess, we solve for the particular solution, we put it together with the homogeneous solution, and then we use any initial conditions to solve for the C1 and C2 to get our absolute and complete final answer for a problem. So a lot of stuff in this video. Definitely pause it, go back. If any parts are weird, shoot me an email, post in the discussion, and I will get back to you ASAP.